Hey, welcome back. This is now officially Chapter 9, 9.1. We're working with sequences, and so it's going to kind of coincide with limits, like the way you learn limits. You kind of, if you have a limit, like a limit of 1 over x as x goes to infinity, you think of this kind of as a sequence, right? You can make, and that was kind of when we introduced it in Calc 1, it was like an analytical method. So you would have x, and then you kind of look to see where 1 over x goes. But you would think of it in terms of a sequence, right? You wouldn't think of it as kind of a continuous spectrum. So, you take x values going to infinity, so like 10, 100, and that's a sequence right there, 1,000, etc. And then you're plugging these numbers into here, and you get another sequence: 1/10, 1/100th, 1/1000th. Okay, so you've kind of already been working with sequences to a certain extent. We're going to make it more strict at this point. We'll see there's another strict definition of a limit coming up, and okay, so let's dive in there and take a look. Okay. So section 1 will begin with kind of a definition, the definition of a sequence. And basically it's a function where your domain, instead of being all real numbers, it's going to be some subset of the integers. Okay, so a function where the domain is a subset of the integers. Usually we're talking the non-negative integers like 1, 2, 3, 4, 5, 6. We won't include the negatives. Okay, you might include 0, but you won't include -3, -4, -5. No. Okay. So, anyways, we need some notation. So, an example here of a sequence: 1, 3, 5, 7, 9, blah, blah, blah. And then this thing here, 2n minus 1, and then blah, blah, blah. Okay, so this guy here is the first term. So you may be able to guess that, right? And we'll label it a sub 1. This guy here is, guess what, the second term. And we can label that a sub 2, et cetera, the third term, fourth term, fifth term. This element here is the nth term. And it's basically a formula that tells you how to produce these numbers in this sequence. Okay. It's similar to what you did with functional notation. It's just, it looks a little different. So here, our nth term formula, a sub n, is 2n minus 1. But you can compare and contrast that with f of x equals 2x minus 1. Okay, they're basically the same thing. It's just we use kind of the an to remind you that we're working with a sequence such that where the domain is some subset of the integers. Right? Over here with f of x, it was a continuous stream of values. And you could even plot these, right? So if I were to plot a sub n, a sub 1 is going to be 2 minus 1, which is 1. So you'd put a dot there. A sub 2 would be 4 minus 1, which is 3. So you'd put a dot there. A sub 3 would be 6 minus 1, which is 5, so you put a dot there. So if you plot a sequence, you just get a bunch of dots, and you compare that to a plot of the actual function, and of course our, wait a second, is 1 really 1? Yeah, it is. 1 is at 1. Seems like, it looks like it's going through 0, 0. It doesn't. Okay? The actual line intercept is at -1. But, anyways, if we were to plot this thing and on the real numbers, it would look something like this, right? But the point is the sequences are on the set of some subset of the integers. Okay, so you just get all these dots instead of a straight line. Okay, so the entire sequence, if we have to give it a name, if we talk about it, we won't say A sub n. We're going to say the entire sequence is denoted curly bracket A sub n. Okay, let's dive right in here and kind of look at some of the introductory exercises. And first, all they want you to do is list terms. Okay. So they're going to give you an nth term formula for the terms of the sequence and ask you to kind of just write out the first 5 terms. Okay. So write the first 5 terms. Okie dokie. So we have A sub n equals -1 to the n times 2/5 to the n. Okay. So it's a little bit different than our usual functional looking expressions like you would see in algebra and stuff, especially this -1 to the n. But all that -1 to the n is going to do is kind of flip-flop the sign as you go through the terms of the sequence. Okay. And listing out terms, it seems like a silly process, but one thing you're doing is kind of learning how these are structured, because later in life you may be asked to kind of come up with these expressions on your own based off of a pattern. Right. So anyways, A sub 1, how do I figure that out? Well, you're just going to replace n with 1. It's basically just, substitute in 1 for n. So you get -1 to the n times 2/5 to the 1, which is -2/5 at the end of the day. A sub 2 then, -1 squared, so that'll become positive, and then you have 2/5 squared, so you get 4/25. A sub 3 is going to be -1 cubed, so now it's going to be negative, times 2/5 to the 3rd power, so -8/125. A sub 4 will be -1 to the 4th times 2/5 to the 4th, which will be positive now, 16/625. And then A sub 5 will be -1 to the 5th, so it goes back to being negative, times 2/5 to the 5th, which will equal -32/3125. Okay? Okay, so when it alternates back and forth, you call that alternating, believe it or not. And we'll see those kinds of sequences again later on, alternating. What they call it. Well, the kinds of sequences we want to look at in particular are sequences of partial sums, and we'll talk about that later. So in this section, we're kind of introducing you a particular kind, or we're just talking in general about sequences, but for our work, there is a particular type of sequence that we're interested in. So, I mean, you can literally go online and become like a sequence specialist, right? So you can go to the internet, it's called Online Encyclopedia of Integer Sequences. Is it there anymore? Encyclopedia of Integer Sequences. This is kind of, it used to be a book, and it was made by some guy from Australia. I got to see him at a math conference once. I got to see Wolfram too. I haven't actually met him, but I was in the same room with him and everything. But anyways, you can go here and just play around with sequences. I actually have, I've created 2 sequences myself. Back in the day, if you created like 3 sequences, they would send you a certificate in the mail. But you can see that 16 years ago, I was more into this than I am now. So those are my sequences. So anyways, you can also kind of put in sequences and it'll give you formulas like the one we're working with right now, 1, 3, 5, 7, and then search it. And it'll give you other sort of expressions which will give us that sequence. And yeah. Okay, so fun stuff. People really get into it. They get into these puzzles. People love puzzles. If you get into puzzles and solving puzzles, you might want to go work at the NSA and do cryptology or something. But you don't have to work like for the government. You can work for pretty much any internet security people. They're going to be interested in that kind of stuff. But anyways, yeah, interesting stuff. Okay. What do we want to do with these things? Our goal is to kind of see where they go as they go to infinity, if they kind of level off at one place. So you can imagine maybe plotting a sequence, and with our little dots, and here's at 1, and then I'll just get a bunch of them, right? I want to see where it goes as n goes to infinity. So maybe this sequence kind of looks like this. And it kind of looks like it's leveling off, right? It kind of looks like it's getting really, really close to some number. Those are the ones we're going to be interested in, because those are going to be useful to our work. If they don't really go somewhere, in other words, if you kind of, if it's kind of like always alternating, jumping back and forth, and it never really settles on something, those are not going to be useful for our work. So we want to know when these sequences converge, and you probably heard that term before in the 8.8 section. And we want to know when the sequences diverge. Okay, so the convergent ones are going to be useful. The ones that have limits are going to be useful. Okay, the ones that don't are not. So it really comes down to looking at the limits of these things, and it all goes back to what you kind of already know from Calculus 1, at least in the beginning. Okay. So we're really going to be looking at the limits of these sequences, and you could kind of already even take a mini limit here. So where does this sequence go? The limit as n goes to infinity of 2n minus 1. Does it go anywhere? Well, no, this thing is going to go to infinity, right? And you could compare that to the limit as x goes to infinity of 2x minus 1. Okay? They both are going to go to infinity, right? So we would call this one divergent and pretty much say it's not useful for our work. But something else, like maybe this guy right here, is actually going to be convergent. It's going to get really, really close to 0. Believe it or not. So this limit will be something that we will, this kind of sequence would be something that's more useful. Okay, so anyways, it's limits. Okay, we want to know where these sequences go as they go towards infinity. Do they go anywhere or not? We'll have to again reintroduce this idea of a strict definition. So you may remember this from Calc 1. You may have learned to hate it in Calc 1. The strict definition of a limit. Okay, the definition you see in Calc 1 is kind of not, it's more powerful than what we're doing here. Like if you took an advanced calculus class where they kind of build calculus from nothing, they start here in sequences with limits of sequences, and then eventually, after like a year or two, you'll end up looking at limits of functions. It's kind of backwards the way we've taught you, but we don't want to spend 8 years trying to just build mathematics from the ground up, right? So we kind of just gave it to you. But anyways, there's a strict definition of limit. So the old limit definition was for every epsilon greater than 0, this is just a delta greater than 0, such that for all x that are within some delta distance of some c value, the distance between f of x and L is less than any epsilon you can imagine, right? So the strict definition of limit here, a little bit different, because we're dealing with the kind of limits we're interested in are always going to be infinite limits. We don't really care about like the limit as x goes to 3 and things like that. We just care about as x goes to infinity. So anyways, without further ado, the strict definition of a limit. So we have the limit of a sequence. A sub n is L, which we write as the limit as n goes to infinity of whatever your A sub n formula is equals L. If for any epsilon greater than 0 that you can imagine, there exists some m value greater than 0 such that if the term of the sequence that, like a sub 10 is bigger than this m value, so maybe the m value is 3 or something. So if n is greater than this m value, then the distance between the terms of the sequence and this number L will be really, really small, okay, less than epsilon. Okay. So what that means geometrically is that for any epsilon value you pick around this thing that it looks like it's getting really close to, so maybe L plus epsilon up here, L minus epsilon down here, you can go far enough out in the sequence such that all the terms in the sequence are kind of in any epsilon interval that you can kind of imagine, right? So the m value here for this particular epsilon is pretty small, but there exists an m value for any epsilon that you can imagine. So clearly, once we get past this m value here, all of the a sub n terms of the sequence will be within those two blue dashed lines. Okay, and that visually we can just see the truth of that. Okay, so the strict definition of a limit says that for any epsilon you pick, and no matter how close you get to this L, you can always go out far enough and find this m value such that all the terms of the sequence past that m value will kind of be within this little channel built by the epsilons. Okay, so when this limit exists, we call it convergent. So if, let me erase that. If the limit exists, we say it is convergent. The sequence converges. It is converges. No, it is convergent. Otherwise, we're going to say it diverges. Otherwise, it diverges. Okay, so in our work, convergent is good, divergent is bad. Okay, section 4 then. It turns out we're kind of going to sweep this definition under the rug. If you like things like this, I encourage you to go to grad school or just keep taking calculus classes. They'll beat it into your head. And you'll spend a lot of time working with it. It's almost like you don't do math anymore. It sort of turns into logic with some math ideas sprinkled in there. But anyways, if you like that kind of stuff, take like advanced calculus. They have classes called advanced calculus. Take real analysis, things like that. Anyways, we're not going to have to worry too much about this definition. It'll come up in proofs. So there's a lot more proofs in Chapter 9 than usual. And it really gives you a flavor of what it's like to do more advanced mathematics. So I always kind of, when I was younger, I didn't really know that about math. I mean, I liked geometry and doing proofs there, but it turns out if you keep taking math, you do less and less computations and more proofy type stuff. And I think a lot of it has to do with the fact that you could train computers to do most of our computations at this point. And it's even getting now to the point where you could train computers to do proofs, to work on stuff like this that kind of, and back in the day the computers couldn't do it. But anyways, we're kind of going to sweep it under the rug. I'm not going to, I think in days past I do extra credit with regards to this stuff. You use it, but you use it in proofs. Okay, you use it to prove other things about limits. And okay, the truth is though, a lot of the way we deal with limits just comes from the methods we learned in Calc 1. Those methods are more powerful than the methods here, so we can apply those methods here. Okay, so the first sort of trick in our toolkit for finding limits will be just anything in Calc 1 kind of applies here. So use your Calc 1 methods. Okay. So for example, maybe you have a sequence a sub n equals 1 over n, right? So we can easily take the limit of that by noting kind of the calculus version. So the limit as x goes to infinity of 1 over x, we should all know, it's 1 over 10, 1 over 100, 1 over 1,000. It's going to get really, really close to 0, so it goes to 0. So if back in Calc 1 we would have that goes to 0, it forces this thing to also go to 0. Hence, the limit as n goes to infinity of 1 all over n will equal 0. And geometrically, you can kind of assume that because, the function 1 over x as x goes to infinity, you can see it gets really, really close. And all the sequences is kind of a light version of that, right? So the sequence is basically just a bunch of dots. And you can see that the dots are going to be forced to get really, really super close to the x-axis. Because the function the function over the reals is getting really, really close to the x-axis, and the function over the integers is just kind of a subset of that. So at least geometrically, I think you can stomach this notion, right? So a lot of these limits you're going to be able to handle. Let's look at one, maybe a sub n equals n minus 1 all over n squared plus n, like that. Okay. So the limit of this thing back in Calc 1 as x goes to infinity, and we're always going to do x goes to infinity in this section, or n goes to infinity. So I replace the n's with x's. So how did we do this? We just kind of, looked at the behavior of the high degree terms. That would be 1 over x. It's x over x squared, but that's 1 over x. So again, this would go to 0. Hence, our limit now with sequences also goes to 0. So you should be able to look at things like that and just kind of automatically know based on our work previous. So the limit as n goes to infinity of negative 3n cubed plus 2n minus 1 all over 5n cubed minus 2n plus 1. You should be able to look at that and say that's negative 3/5. Okay? I hope you can do that. You can also do L'Hopital's. So another example. We have a sub n equals the ln of n cubed all over 2n. Technically, you can't do L'Hopital's on a sequence. The derivatives and stuff won't work there because it's just a bunch of points. But you can take the limit with respect to x, and then that will force this limit of a sub n to go to the same place. So you have ln of x, let's use the power rule of logs to bring the 3 up in front, all over 2x. And we can see that's infinity over infinity form, so we could do L'Hopital's. So you get 3 all over x all over 2. So that's the limit as x goes to infinity of 3 all over 2x, which again is L over infinity, which is always just 0. Okay. So hence the a sub n stuff will also go to infinity. Okay. ln of n cubed all over 2n equals 0. For the sake of sanity, you don't have to take the limits in terms of x and show me that and then say hence the limit as n goes. You could just kind of put the n in for x and do your calculus there. Technically, you're not allowed to do that, but I'll let you get away with it for the sake of sanity. Okay. Okay. What else? So the squeeze rule was a Calc 1 method. It'll end up working here as well. So Squeeze Theorem. Basically, if you have the limit of 2 sequences as n goes to infinity going to the same place, so let's say the limit as n goes to infinity of a sub n is L, and then that equals the limit as n goes to infinity of some other sequence, call it b sub n. And so it's not just this. If this is true and oops, got the wrong color. And you also have the inequality holding a sub n less than or equal to c sub n, so c sub n being some third sequence less than or equal to b sub n for all n eventually. So it doesn't have to hold at first, but it could just hold eventually for all time. If these two factoids are true, so if those are fulfilled, then the limit of c sub n as n goes to infinity goes, guess where? Well, it goes to L, right? So if you have something like this example, a sub n equals sine of n all over n, you can force that to go, it'll go to 0 because you note that sine of n over, well just sine of n first off, is the sine of x is less than or equal to 1 and greater than or equal to -1. So sine of n, which is just a bunch of dots, right? So sine of x looks like this. Sine of n is just a bunch of dots on that thing, you know. So it's a subset of the y values are a subset of the sine of x values. So therefore, sine of n is also less than or equal to 1, right? So anyways, once you have this inequality, if you assume n is greater than or equal to 1, you can divide all three sides by n. Okay, so we can't divide by 0, so you kind of have to say, well, we need to make sure n is not equal to 0. So if you divide everything by n, you get this set of inequalities. And then you can take the you kind of know what the limit on the sides are, right? So I note the limit of -1 over n as n goes to infinity. That's just L over infinity, so that's equal to 0. And the limit as n goes to infinity of 1 over n is also L over infinity, which is equal to 0. Hence, it forces that middle sequence to also go to 0. So hence, the limit as n goes to infinity of sine of n all over n will equal 0. And so we got it. Okay, great. What else? You're going to see sort of sequences that are kind of, okay, so let me show an example. A sub n equals, let's say, -1 to the n plus 1. Okay, so what the heck is this thing? A sub 1 will be -1 to the 1, which is -1 plus 1, which will equal 0. A sub 2 will be -1 squared, which is 1, plus 1, which equals 2. Okay. A sub 3 will equal -1 cubed is -1, and then plus 1, which equals 0. A sub 4 will equal -1 squared, so that'll be +1 at the end of the day, and then plus 1, which equals 2. So you see in a pattern here, a sub 5 must equal 0, and then a sub 6 must equal 2, right? So it seems like it's not going to converge. If you kind of think of the picture, you know, you're going 0, or we're starting at 1, right? So 0, 2, 0, whoops, I shouldn't have put those right over each other. 0, 2, 0, 2, 0, 2, 0, 2. So there's no L number that this thing's getting really close to. I mean, you force the L to be over here. There's no M that you go past that, where you're going to be within 1 of L, because it's always going to jump out to 0. If you tried to say the limit is 0, there's no M that you could go past, such that if you're given epsilon equal 1, that it's going to stay within 1, because it's always going to jump up to 2. So there's no way to get this thing to have a limit, but it's not necessarily something that you can easily communicate to your grader. Okay, so what I suggest people do is to kind of, you know, look at what we're dealing with here. The even terms, I'll just say that A sub even, the even term formula is what? Well, here's 2, it's always 2, right? So you could say A sub even is 2, and then look at A sub odd. A sub odd is what? Well, it's always 0, right? So it's 0. Then take a look at the limits of A sub even and A sub odd. The limit of A sub even equals 2, which does not equal the limit of A sub odd, which equals 0. And I want to give that to you as a theorem. Okay, I'm just going to tell you that you can hit that button anytime you want, basically. And I guess this would be part C. If that looks like a G, but it's C. If the limit of the even terms does not equal the limit of the odd terms, then you can conclude the limit of the sequence does not exist. End of story. Okay? So that's like a theorem you could use. I think before in Calc 1 we would just say it's oscillating. Like we had some functions like the sine of x as x goes to infinity, and you can make sort of a sequence of values that would never converge to anything, a subsequence, and that holds true for here. If you can find like a subsequence that kind of doesn't converge, it'll imply that. And there's all kinds of weirdness associated with this if you keep studying math. Like, what was it? It was like Cauchy sequences and stuff like that. I've not really studied that in a long time, so I don't want to get myself in trouble. But this one you could use. Okay, I'm giving you the go-ahead to use this theorem. So, anyways, let's look at another example. A sub n equals -1 to the n times n all over n plus 1. Okay. So in this case, the even powers, well, so if you have a sub, I guess, 2n, we could write it like that, which, is really the even stuff. It's going to be -1 to the 2n times 2n all over 2n plus 1, right? So what is that? Well, -1 to the 2n is the same as -1 squared to the nth power times 2n all over 2n plus 1. And then that will equal -1 squared is +1, and 1 to any power is just 1, okay, times 2n all over 2n plus 1. So a sub 2n is just 2n all over 2n plus 1, and we could take the limit of that, right? We know how to do the limit of that character. So the limit of the evens, basically, as n goes to infinity, will be the limit of 2n all over 2n plus 1, as n goes to infinity. And then our superpowers from calculus allow us to just look at that and note the limit is 1. Okay, okay, let's look at the odd ones then. So 2n plus 1 or minus 1. Depending on whether you're starting at 1 or 0. If you start at 0, we'll use 2n plus 1. That way we start at a sub 1. What is that? Well, that's -1 to the 2n plus 1 times 2n plus 1 all over 2n plus 1, which is 2n plus 2. Right? I'm just plugging in 2n plus 1 for n into this expression, and well, the whole expression, right? Wherever I see n, I put 2n plus 1. Okay. So simplifying this, and again, it comes down to kind of simplifying this part of it. So what is that thing? That's -1 to the 2n times -1 to the 1, right? So that's just the product rule for exponents. You have a to the x times a to the y. That's the same as a to the x plus y, and vice versa, right? We just sort of started with a to the x plus y and went to a to the x times a to the y. Okay. So then this will be, well, negative 1 to the 2n, we kind of already figured that out to the left here. Negative 1 to the 2n is just 1 to the n, which will be 1. So you just have 1 times negative 1 to the 1, which will end up being negative 1. So that thing is just negative 1. And so you get negative 1 times 2n plus 1 all over 2n plus 2. We could distribute the negative 1 to the numerator, if you wish, and you get negative 2n minus 1 all over 2n plus 2. And then you could take the limit of that character, right? So in this case, the limit of the odds will equal the limit of negative 2n minus 1 all over 2n plus 2 as n goes to infinity. N goes to infinity. And then from our superpowers, we're able to kind of look at just this part. Negative 2n over positive 2n is negative 1. And so the limit of the odds is not equal to the limit of the evens, and hence the limit of the sequence does not exist. Okay. One thing to note is I believe that sort of if the limit does exist, it forces the limit of the evens and the limit of the odds to be equal. Okay. Okay, but I'm not going to introduce that, as I don't think it's really required at this point. Okay. What else is there? The absolute value theorem, another sort of theorem we could use for proving limits. Absolute value theorem. And in this case, how the heck does this one work? Well, we say if the limit of the absolute value of the terms of the sequence as n goes to infinity actually equals 0, then the limit of just plain old a sub n, the original sequence that you're dealing with, will equal 0 as well. Okay. One thing to note is kind of how absolute values affect these negative 1 to the n things. So, for example, let's say I have the absolute value of negative 1 to the n. Well, no, let's kind of let's look at, let's see if I have an example. Yeah, I do. Okay, so let's look at a sub n equals negative 1 to the n all over n. Okay, and over here, let's look at the absolute value of a sub n equals the absolute value of negative 1 to the n all over n. I claim that taking the absolute values will clear out any of these pesky negative 1 to the n things. So automatically you can write 1 all over n like this. And then if n is always positive, you can reduce that to 1 over n. Okay. That's what I claim. I claim a sub n is actually equal to 1 over n. So maybe we should also kind of include a third sequence. Let's say a sub, or no, let's call this b, right? Call this b sub n, which is just 1 over n. And let's look at how all these guys behave. Okay, so this guy, a sub n is negative 1 to the n. A sub 1 will be negative 1 to the 1, which is negative 1 all over 1. A sub 2, which is negative 1. Okay. A sub 2 would be negative 1 squared, which is positive 1 all over 2, which of course is just 1/2. I don't know why I wrote that twice. I'm just trying to get things aligned. Okay. A sub 3 will be negative 1 cubed, which is negative 1 all over 3. I guess I don't really need to, sorry. A sub 4 will be negative 1 to the 4th power, will be positive 1 all over 4. You getting the idea here? Let's do one more. A sub 5 will be negative 1 to the 5th, which is negative 1 all over 5. Okay, that's good enough for now. Let's look at this thing. Okay, so a sub 1, the absolute value of a sub 1 is going to be negative 1, absolute value of negative 1, which will equal 1. absolute value of a sub 2 is just a sub 2. Absolute value of a sub 3 is 1/3. Absolute value of a sub 4 is 1/4. Absolute value of a sub 5 is 1/5. Okay. And then finally compare that to b sub n. So b sub 1 is 1/1, which is 1. B sub 2 is 1/2. B sub 3 is 1/3. B sub 4 is 1/4. And I think it's clear that b sub n, 1/n, is equal to a sub n. So long story short, if you see one of these pesky -1 to the n's and it's inside of an absolute value symbol, you could just throw it in the trash. I don't care how complicated the expression looks. You could have something like the absolute value of -1 to the n plus 1 all over 2, sine of x divided by -1 to the n minus 1 times e to the x times -1 to the 2n minus 1 all over -1 to the 3n. Absolute values. The absolute values will clear out all of that -1 junk. Okay? And you'll end up with just the absolute value of everything else. Sine of x over e to the x. Okay? Okay. So there's my little spiel on that. Anyways, getting back then to the absolute value theorem, let's take a look then at this example. So we have a sub n. A sub n is equal to -1 to the n all over n. Okay? The absolute value of a sub n is equal to just 1/n, which we've shown. The limit of 1/n as n goes to infinity is 0. Hence, from the absolute value theorem, the limit of -1 to the n all over n is equal to 0 as n goes to infinity. Okay, so that's the absolute value theorem. The absolute value theorem, the proof of it is kind of clever. So I just want to show you the proof really quick. It uses the Squeeze Theorem. So I said there's a lot more proofs in this section. Let's make this, no, let's not make this the video quiz. I'll give you the video quiz here in a little bit. So anyways, we assume, so when you're doing a proof, you're trying to prove an if-then statement. What you do is prove the if part. You assume the if part, and then you prove the then part, right? So what we want to do is assume the if part, and then we use algebra theorems that have been previously established and anything that you kind of have accumulated as a math person. So algebra, just algebraic facts, math facts, common sense, math sense, I guess. Theorems. Okay. You use all of that stuff to try to connect the dots to the then part of the statement. So we want to start with that red box and finish with the blue box. Okay, so we make that red box a supposition. We suppose it's true. We assume that it's the given part. If you ever taken like geometry, they always talk about the given information. That's your supposition. That's what we start with. So we assume or we suppose the limit of the absolute value of a sub n as n goes to infinity equals 0. Okay. Next is kind of the math common sense. And I think you'll find, embarrassingly enough, that as a student, you probably don't have a lot of math sense. I find I myself have more street sense than math sense at times, and it's embarrassing, okay? It really is. So you need to work on your math sense. Everybody does. So anyways, next we note this following sort of mathematical fact that is common sense, but again, like I said, you probably aren't at that point where you have a lot of common sense mathematically. Okay, look at this thing. That's not something you would normally think up, right? But it's common sense. You know, if you have 5, that's going to be greater than or equal to negative absolute 5, but less than or equal to absolute 5. And that's true for anything, any number you can imagine. You know, pi is greater than or equal to negative absolute value of pi, less than or equal to pi, absolute value pi. Okay, so it's common sense. Duh. Okay, so what? Well, now you can kind of use the squeeze theorem. So next, we apply a theorem that we've previously established. So next, we note the limit of the two ends of the compound inequality. So we note the limit of the negative absolute value of n as n goes to infinity equals, and we can factor out the negative, so we get negative limit as n goes to infinity of the absolute value of a sub n, and then from our supposition, you know, our supposition right here, we know that's true. I mean, we know that equals 0, right? It's negative 1 times 0, the negative from the front that we factored out. Negative 1 times 0 is 0. Okay. Also then, the limit as n goes to infinity of the absolute value of a sub n is equal to 0. And again, that's from the given information. So hence, by the squeeze theorem, we can conclude the blue box, the limit of a sub n as n goes to infinity equals 0. Okay. Okay. So it needs to, when you do a proof, you need to write it out so people can understand what the heck you're talking about. And it really, you know, it seems kind of mystical and magical, but it's just thinking out loud and writing it down and having it kind of make sense. Okay. You use common sense, so we all have sort of an innate sense of logic and what is possible and what is not. It's just calling upon that common sense, summoning. You know, this step right here, it's almost like a bridge too far right now, you know? But it's so obvious. It is so clear. It's just common sense, a lot of this proof stuff. And, I mean, try to teach that to a computer, right? So anyways, there's that. Let's move on. Okay. The last section, our ultimate goal is to prove that, that if something is... so in this last section, what we want to prove is that if a sequence is kind of increasing and bounded above, it's convergent. In other words, if you take the limit of it, you'll get some number out. You may not know what the number is, but these theorems are going to tell you that they are, in fact, convergent. So a lot of times in math, and I've probably said this before, a lot of times in math, it's like looking for a needle in the haystack, except sometimes the needle is not actually in the haystack. So you're looking for a needle in the haystack, but you don't know if that needle is actually in the haystack. And on top of that, you don't know if you have the ability or the tools to find that kind of needle, because maybe the needle is actually invisible. So you're looking for an invisible needle in a haystack. The needle may or may not be there, and on top of that, the needle may be invisible to your eyes, the way you're trying to look for it. So that's math in a nutshell, in my opinion. Anyways, this will say the needle is in the haystack. Okay, you may not have the tools to find the needle. You know, maybe you're using some sort of X-ray machine, but the needle isn't X-rayable. but it's definitely there in some way. Okay, so anyways, one fact is if it's increasing and bounded above, it's convergent, but also if it's decreasing plus bounded below, it's convergent. Okay. In order to pull this off, we need to kind of worry about these words increasing and decreasing, because we can also include sequences that kind of don't increase, but rather kind of stay the same. Okay, so there's in some books they'll talk about strictly increasing. In our book, we talk about non-decreasing as increasing, which is really weird. Okay, so increasing, here we'll talk about that as non-decreasing. That way we can include these things that just stay the same. Okay, and then we'll say decreasing is basically non-increasing. And it seems weird, but if we didn't do it this way, we would have to introduce a couple extra definitions, and you would get annoyed about that. Okay, this is a no-win situation. Otherwise, we wouldn't do it. Okay, okay. So this is the first issue we want to deal with, and it's called monotonicity. So there's two types of monotonicity: non-decreasing and non-increasing. Okay, so first, non-decreasing, and we could symbolize this with a chain of inequalities. So for non-decreasing, a sub 1 will definitely be less than or equal to a sub 2, which is less than or equal to a sub 3, etc. Okay. The second one then is, of course, non-increasing. And again, we could represent this via a chain of inequalities. A sub 1 is greater than or equal to a sub 2, greater than or equal to a sub 3, greater than or equal to ... greater than or equal to a sub n, greater than or equal to a sub n plus 1, greater than or equal to ... Okay. We're going to need to prove, not just for this theorem, and this theorem is mainly used in the book for proving other things. Okay. We will need, though, to prove that things are monotonic later in the chapter when we're dealing with alternating sequences. Okay. So we will want to be able to prove that things are monotonic, and so I want to introduce you to those proofs right now because it just seems like a natural place to do it. Okay. And there's basically two types of proofs. There's the algebraic types, which are kind of what they would call a direct proof, and then there's the calculus types where you're looking at the derivative. Okay? So first, the algebraic type proofs are kind of based off on comparing the subsequent terms of a sequence, and then comparing those values to like 0 or 1. Okay? So first, let me call this monotonic proofs, or proofs of monotonicity. So the first type I want to look at are the algebraic types. And what we're doing is kind of borrowing this inequality and manipulating it into a form that we can compare to 0 or 1. Okay, so if you start with a sub n greater than or equal to a sub n plus 1, and let's not fill in the inequality because that's kind of to be determined. Okay, so I'm going to put a box there to indicate we're comparing these. Okay, if you subtract a sub n from both sides and flip sides, you could compare the difference between a sub n plus 1 and a sub n to 0. Okay. So if a sub n plus 1 minus a sub n is greater than 0, or greater than or equal to 0, that implies that the next consecutive term is getting bigger, right? So this means it's non-decreasing. If it's less than or equal to type, that means the next consecutive term is less than the previous guy, and therefore it's non-increasing. So let's look at one of those types. For example, the sequence a sub n equals 3n all over n plus 2. Okay, so I'm going to need a sub n plus 1 minus a sub n. To get a sub n plus 1, all you need to do is plug n plus 1 in wherever you see n. Okay? So you're going to end up with 3 times n plus 1. You have to distribute. It's not 3n plus 1, it's 3n plus 3. All over n plus 1 plus 2. And then minus, because I plugged n plus 1 in for n, and then minus a sub n. And one thing should be noted is we're looking at n values that are in the positive integers. So let's just say n is in the interval from 1 to infinity. We could push out the 1. We could say 8 to infinity, 2 to infinity, 100 to infinity, just so long as eventually the inequality holds forever. Okay, so in other words, maybe a quicker way to write n is in this interval is to just say that n is greater than or equal to 1. Okay, so anyways, here we go. I'm going to distribute the 3, so get 3n plus 1. N plus 1 plus 2 is n plus 3 minus 3n all over n plus 2. Find a common denominator, so 3n plus 1 times n plus 2 all over n plus 3 minus, well, times n plus 2, right? I forgot that. Minus 3n times n plus 3 all over n plus 2 times n plus 3. Some busy work here. So foiling in the first numerator, you get 3n squared plus 6n plus n. So plus, that doesn't seem right. Plus, what did I do wrong? And I made that mistake. There we go. Sorry about that. So 3n squared plus 3n plus 6n is 9n plus 6. And let's just go ahead and subtract the other numerator, right? So minus 3n squared minus 9n when you distribute the negative 3n all over n plus 2 times n plus 3. And then these guys cancel, and you end up with 6 all over n plus 2 times n plus 3. And that's our a sub n minus a sub n plus 1 minus a sub n, and we want to compare that to 0. And we're working for n greater than or equal to 1. Right, so if n is greater than or equal to 1, and this is kind of another common math sense type thing, but you could kind of show it analytically. If n is greater than or equal to 1, you can add 2 to both sides of that. So n plus 2 would be greater than or equal to 3, which is definitely greater than 0. In other words, n plus 2 is positive. Also, if n is greater than or equal to 1, then n plus 3 is greater than or equal to 4, which is greater than 0. So n plus 3 is positive. Well, so what? Well, look at that expression. I have 6 all over n plus 2 times n plus 3. And regardless of what n is, because n is greater than or equal to 1, n plus 2 times n plus 3 is a positive times a positive, which is positive. So at the end of the day, I have a positive over a positive, and a positive over a positive is positive. So if I wanted to write out like a real hardcore technical proof, I would have to write all of that out. And it's kind of obvious, but it gets swept under the rug, right? It's like common sense, but you're not used to having to do that. And it literally is just kind of trying to move your inner thought that's been beaten into you over years of arithmetic into this outer realm where we can all appreciate your genius. Okay, so it's very hard to do, and it's probably one of the reasons why computer programmers have a hard time using computers to prove things, because we're not used to pushing out that kind of thought, so computer programmers can analyze it and code it. Okay, in my opinion. Okay, so anyways, this is a positive over a positive. In other words, it's greater than 0. It's greater than 0, and therefore it's also greater than or equal to 0. So what's happening here is that the next term in line is always bigger than the previous term. In other words, it's non-decreasing. Okay. So that's the first type of proof for monotonicity with the a sub n plus 1 minus a sub n. The next kind of proof, the second kind of algebraic proof, that is derived from this blue box inequality. So again, this is kind of taking that blue box inequality. I should have given this another heading, but what do we have? A sub n plus 1, and we're comparing it to, well, it was going in the other direction, right? So a sub n compared to a sub n plus 1. This time, instead of subtracting a sub n, we're going to divide both sides by a sub n. So the resulting inequality that we're going to be looking at will be a sub n plus 1 divided by a sub n, and we're comparing that to 1. Okay. So if this is greater than 1, that means that the next term in line is greater than the previous term, right? So if it's greater than 1, greater than or equal to, that will automatically imply it's non-decreasing. Right? If it's less than or equal to 1, that means that a sub n plus 1 is less than a sub n. So in that case, it'll be non-increasing. Okay. So the next question is the video quiz. Okay. So video quiz question, video quiz question, video quiz question, video quiz question. Hopefully I don't screw it up. We want to show that this thing is, is it monotonically, is it monotonic, is it non-decreasing, or is it non-increasing? Okay, so what do we need to do? We need to make a ratio of a sub n plus 1 and a sub n. A sub n plus 1, again, all I'm doing is plugging n plus 1 in for n. So we'll have 2/3 to the n plus 1 power. And again, let's specify the range of values for n. So n is greater than or equal to, we'll say 1. Okay, and then that's all over a sub n, which is 2/3. 2/3 to the n. And then we can use our quotient rule for exponents, right? If you have a to the x over a to the y, that's equal to a to the x minus y, right? So we'd have 2/3 to the n plus 1 minus n, which is 2/3 to the 1, which is just 2/3. And then we're comparing that to the number 1. What is that? Well, that's less than, so therefore also less than or equal to. In other words, the next term in line, a sub n plus 1, is smaller than the previous term. In other words, it's non-increasing. Okay, so that's the video quiz question. Prove whether or not this is increasing. Determine if it's increasing, non-increasing, or non-decreasing. And we just found it's non-increasing. It's a very important type of proof, and again, like I said, we're going to be using that later in the alternating series section. Okay, so those are the algebraic proofs. Then come the calculus proofs. Okay? Calculus proofs for monotonicity. And what it comes down to is you're given a sequence, and then you'll take that sequence and convert it into a function. And then you'll take that function and take the derivative, and then you're comparing the derivative to 0. So if it's less than or equal to 0, that means it's non-increasing because it has kind of a negative slope. If you think of like a derivative as kind of like a slope. And then greater than or equal to 0, that will imply it's non-decreasing because it has kind of a positive slope. Okay, so you usually use the calculus methods when everything else is failing on you, because they kind of will tie your hands later on if you go into like an advanced calculus class. They'll say, well, you're not allowed to use calculus because we haven't proved anything in calculus yet. So you have to use non-calculus methods like I did for the algebraic proofs. But for us, we can use calculus. And in particular, something like this, the algebraic proofs would be a nightmare. Okay, so the calculus proof for monotonicity would be a lot easier. So what we do first is convert it into f of x. We have x equals negative x over 2. And I'm going to say let n be greater than or equal to 3 for reasons to be shown later. Why not 1? Well, I'm going to show you later. Okay. And then f prime of x is going to be, you have to do a product rule, so the derivative of x is just 1, and then I have e to the negative x over 2, plus leave x alone, take the derivative of e to the negative x over 2, which is e to the negative x over 2 times negative 1/2. Okay. And then you have to find the critical points, right? Because it could be increasing and then decreasing, and all we care about is eventualities. If it's always eventually decreasing, that's good enough for us. We'll say it's non-increasing. Right? If it's always eventually increasing, good enough, we'll say it is always non-decreasing. Okay? Okay, so we find the critical point, set it equal to 0, factor this ugly thing. So factor out a negative e to the negative x over 2. We have 1 minus 1/2 x. This part will never be 0, but you could take this thing and solve for a critical point. 1 minus 1 over 1/2 x is 0. Multiply through by 2. 2 minus x is 0, so x is 2. And that's why I'm starting beyond 3. Because I know that because the only critical value is at 2 and there's no kind of like asymptotes or anything to deal with, because the only critical value is at 2, if I just go beyond 2, it's always going to have the same kind of behavior. It's always going to be going up or always going to be going down. Okay, okay, so you could still do your little kind of sign chart, you know, starting at 0, or maybe even at 1, and then here's the critical point at 2, and then you could do your test values and your signs and your conclusions. If x is 3/2, plugging 3/2 into the derivative, I have something positive. This is always going to be positive. Times 1 minus 3/2 times 1/2 is 3/4. That will be positive, so it's increasing. And then try something like x equals 5. Again, the first part is positive. 1 minus 5/2 is negative, so it's going to be decreasing here. In other words, it's eventually always non-increasing. So we can conclude it's non-increasing. Okay, so monotonicity tests, very important for the future. I just want to make sure I give those to you now. You may have to look back here for reference. Anyways, our goal, though, back here is to prove that if something is increasing and bounded above, it's convergent, and if it's decreasing and bounded below, it's convergent. We've dealt with the increasing, decreasing parts, the monotonicity part. We just need now to talk about what boundedness means. And it's a fairly common-sensey type thing to understand. Okay, so it's part A, monotonicity. Part B was proofs of monotonicity. Part C now is boundedness. And it kind of means exactly what you would think. It means that the function will never exceed a certain value and never go below a certain value. That's what bounded overall means. But really, there's bounded below and bounded above, right? For example, going back to a sub n equals 2/3 to the n, this thing is actually bounded above and below. You can take a look at the sequence of values. A sub 1 is 2/3, A sub 2 is 4/9, A sub 3 is 8/27. You know it's decreasing, so it's definitely bounded above by 2/3. Okay, we proved it was decreasing above. For the convergence, though, we need to show that when we're dealing with something that's non-increasing, like we have here, or in other words, decreasing, we really need to show that it's bounded below, not bounded above. Okay, so we need to show that this thing is bounded below, and if we could do that, we can prove that it's actually convergent. You know, maybe to what is it convergent to? I don't know. It's 0, but we kind of have to show it's bounded below. Okay, so what can you tell about 2/3 to the n? Well, anything that's positive raised to an exponent will always end up being positive. Okay. It's basically because you're multiplying something that's originally positive by another thing that is positive. So a sub 2, to get a sub 2, we multiplied by 2/3. But to get a sub 3, we multiplied by 2/3, right? So you could probably do some sort of induction proof, and I'm not going to go there. I don't like doing inductive proofs, so I'm not going to force you to bear witness. But I think it's clear. I think we can just say, for me and you, by common sense, maybe in like a proof class you have to prove these common sense things. But for me and you, I'm going to say we can certainly say it's bounded below, right? Bounded below by 0, just because of common sense, I would say. Okay? It's bounded below by 0. So anyways, what do we have then? Anyways, we've shown that it's non-increasing. And then secondly, we've shown it's bounded below. Hence, it's convergent. To what? I don't know, but it's convergent. And it turns out it's convergent to 0, pretty much any fraction r that's in between 0 and 1. If you take the limit of that thing, r to the n, as n goes to infinity, that will equal 0. And you could prove it using calculus. You could say, well, the limit as x goes to infinity of r to the x will equal the limit as x goes to infinity of, you could probably rewrite it as an exponential, right? So you could rewrite it as e to the x ln r, where ln of r is going to be negative if r is in between 0 and 1, right? Because of the plot of the natural log function. So here is 1, and then here is 0, so the y values are always negative. So this thing is less than 0. So what you end up with is the limit as x goes to infinity of e to something that's negative x-ish. Okay, so this is like, or will behave like this thing right here. And then the limit of e to the negative x is the same as the limit as x goes to infinity of 1 over e to the x, which would be 0. Okay. Okay, so there's my sort of calculus proof. The algebraic proof would be much more difficult, no doubt. You would have to prove probably some sub-facts, and then eventually you could prove this fact. But we obviously don't have time because I'm kind of getting, I think this video has been long enough. Anyways, we want to prove this factoid, okay? And that is not an easy thing to do. the proof of that monotonic bounded sequences are convergent relies on something called the Axiom of Completeness, which we don't even have yet. So kind of just thrown in to make your life even more miserable is the Completeness Axiom, which is kind of another one of our common sense facts that you wouldn't normally think of using, but it turns out that we use it. And I don't think it's proved necessarily, and that's why it's called an axiom. We just sort of suppose it's true regardless of whether anybody can prove it's true, and go on as though life is fine and dandy. So anyways, the completeness axiom is going to say if a set, regardless of any of that, if a set of numbers is bounded above, there will exist a least upper bound. So for example, the set, so a sub n equals, what were we dealing with, 2/3 to the n. This sequence is bounded above by the set, let's call it U, all kinds of junk, right? So it's bounded above by 2/3, it's bounded above by 5/3, bounded above by 1,000, bounded above by 99. There's a set of upper bounds. And what the completeness axiom is saying is that there is a least upper bound. So you could basically take, I guess, the min of all the maxes, and you get your least upper bound. And you study that in advanced calculus and real analysis. Okay? You study these least upper bounds. There's also the greatest lower bound, which is kind of like the same spiel. There will also exist a greatest lower bound, which is like the max of all the mins. Okay, so for example, again, I don't want to put that in curly brackets, a sub n equals 2/3 to the n. There's a set of lower bounds, right? So negative 1,000, negative 55, negative 1/3, 0, 2/3. And what the axiom of completeness says is that there will exist a maximum for this set. There's going to be, and I shouldn't say maximum because it seems like that word only applies to finite sets. It's been like 20 years since I've taken real analysis, so please forgive me, math people in the universe. Anyways, hopefully that kind of makes it make sense. I don't think it's a perfect introduction, but that's kind of the idea that this thing is. And you could use this axiom to prove all kinds of neat junk. Okay, and so we're going to use it to prove that monotonic sequences, monotonic bounded sequences, are convergent. Okay, and this is going to be kind of weird. It's a little different, and it might be frustrating, but just think of it. If this is something that a computer would have a hard time doing, which means that you may still have a job when you get older. Computers put everybody out of jobs. They put factory workers out of jobs, and now they're putting brain people out of jobs too. So mind workers. Anyways, let's take a look at it. So basically, the monotonic convergence theorem and in order for this to work out, we need that axiom of completeness. But we also are going to need the strict definition of a limit. Because we're trying to show that the limit exists. So we're going to use the axiom of completeness and the boundedness and the monotonicity in order to kind of build the epsilon definition for the limit. Let me remind you what the epsilon definition of the limit is. It says we have that the limit as n goes to infinity of a sub n equals some number L if for every epsilon greater than 0 there exists an m greater than 0 such that if n is greater than or equal to m, you could usually use greater than or equal to or just greater than, then the difference between a sub n and L is less than epsilon. Okay, so you're going to see my letters and my variables will kind of hint at where we're headed with this theorem. Okay, so let's go at it. Okay, 1 second. Okay, so monotonic convergence theorem, we're trying to prove that this is true. We'll need that axiom of completeness, and we're trying to construct the strict definition of the limit. If we could construct this definition for a particular sequence a sub n, just given that it's monotonic and bounded, then we have shown that it's convergent. Okay, because this definition, if you could fulfill this definition, it means that the limit exists, and if the limit exists, it's convergent. Okay, we're just going to prove the one case where we have a non-decreasing and bounded above. Okay, so this proof isn't complete, but it'll give you the flavor of what the complete proof would be. Okay, so we'll begin with our suppositions. So we're supposing that our sequence a sub n is, in this case, non-decreasing and bounded above. We also have to make one little simplifying solution or assumption, which we do sometimes just so that it doesn't make the proof longer. Like this video is long enough, right? Okay. Also assume each term is positive. Okay. And positive means greater than 0, so you're not including 0. 0 is neither positive or negative. Okay. So since the sequence is bounded, there must exist some upper bound, right? And we'll call that letter m. Okay, so you can see that that variable. Let me not use m. Let's use big N. Okay, so I don't have. I want to make sure my variables sync with my definition above. Okay, so since the sequence is bounded, sorry, we can say basically, this chain of inequalities, a sub 1 is less than or equal to a sub 2, and we can make the chain because it's non-decreasing, less than or equal to a sub 3, less than or equal to dot dot dot, less than or equal to a sub n, less than or equal to dot dot dot, and of course it's bounded above, so we could say that all of those guys, all of the terms of the sequence are bounded above by m. So m must be greater than or equal to these guys below it. Okay, so next and I didn't mean to use big M, I want to use little n. Okay, sorry. All right, sorry, big N as in nanometer. So I'm going to use that big M later. Okay, so next we use the completeness axiom. So next, by the completeness axiom, there exists a least upper bound. and let's call that guy L. And we can make, again, this chain of inequalities. So next, by the completeness axiom, there exists the least upper bound L. And we note, again, a sub 1 is less than or equal to a sub 2, less than or equal to dot, 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 less than or equal to a sub n, less than or equal to dot, 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 less than or equal to this number L. Okay, so that L is that L that we see in the definition. This is going to be the limit, okay, and it's going to converge to this number L. So we kind of want to build this definition, and to get there, we're kind of have to work with it in the compound inequality form eventually. So if you were to expand this using our knowledge of absolute values and inequalities, you could rewrite it as this. And then you could isolate the a sub n in the middle like this. Okay. So what we're going to do is kind of build this inequality, and then we're going to back engineer this statement in the strict definition. Okay. Okay. So and it's the axiom of completeness that allows us to do this, right? So we then note this following inequality. L for any epsilon, and we're now introducing that epsilon guy. So for any epsilon greater than 0, L minus that epsilon will be less than L, strictly less than L. Okay, okay, now some common sense. Because L is at least upper bound, L minus epsilon is not going to be greater than or equal to the terms of the sequence, right? There's going to be some term that's greater than L minus epsilon. Okay? If that was not true, then L minus epsilon would have been the upper bound. But we're saying L is the upper bound. Okay? So that sort of makes sense. Let me try to write that out. So we know for any epsilon greater than 0, L minus epsilon is less than L. And because L is the least upper bound, there must be some a sub something. So let's say a sub, geez, I'm running out of variables. A sub, let's say I already used big N, big M, but then that seems like it's associated with that one. Let's use A sub S, I guess. I don't know. Sorry. Now I want to use big N, right? Well, no, let's use A sub S. No, A sub M is what I want to use. Sorry. Or A sub big N, rather. Jeez. Okay, sorry. Okay, so we know for any epsilon greater than 0, L minus epsilon is less than L, and because L is least upper bound, there must be some A sub n such that A sub big N is greater than or equal to L minus epsilon. Because if not, that's what I was saying back then. If not, then L minus epsilon would be the least upper bound. Okay, so it's this least upper bound theorem that is saying that this A sub n is kind of greater than L minus epsilon. And then for all, and this is why I probably should have used different letters. This ticks me off. I should have used big M. Yeah, let me use big M. I'm sorry. So for all, so for all n greater than or equal to big M, it must be the case that we have L minus epsilon less than or equal to A sub big M, and then that will be less than or equal to A sub n for all n bigger than big M, because this sequence was non-decreasing. And not only that, and see what we're trying to do, we're trying to build that inequality, that compound inequality right here. Okay. So not only that, we can say that, because the least upper bound thing, this guy is definitely less than or equal to big L, right? All the terms of the sequence, we already said, were bounded above by something. And not only that, because of the axiom of completeness, we could say there's a least upper bound L there. And so what? Well, also then, we could go one step further and say that this is less than L plus some epsilon. And now we've kind of built that compound inequality right here. So we can subtract L, we can now say via just some first get rid of the A sub n. So we can now say for all n greater than or equal to this big M, this A sub n is between, and we can even make the inequality better. We could say that it's A sub n is greater than L minus epsilon, and then less than L plus epsilon, which is the compound inequality definition for the L. You have to obviously subtract L from all three sides. Let's go ahead and do that. So I'll have A sub n minus L greater than negative epsilon but less than positive epsilon. That just implies the distance between A sub n and L will be less than epsilon. And that's what we wanted to show. So we've shown that for basically any epsilon you can imagine. Okay, so I took for any epsilon, you can build this inequality, presuming that your n value is greater than or equal to this big M value. Okay. And that's pretty much it. That proves the limit of A sub n as n goes to infinity exists, and therefore it's convergent. Okay, so hopefully that wasn't so painful. I'm sorry this section was so long. Thanks for watching, and we'll see you next time.